Okay, AP Calculus AB, Unit 4, Day 3 lesson. We're talking more about limits. Limits as we go to infinity, positive or negative. It's something we've done a little bit of on a couple assignments, so we're going to go more in depth into it today. Now, this is there's also a new rule called L'Hopital's rule, and it works for some indeterminate forms. So this is a indeterminate form that we've talked about, which has often been a hole in the graph. But this is another way that you can figure out the answer to this. And sometimes it can be a lot easier than the factoring the hole out. Plus, there's going to be other issues where there's a hole and you can't factor it out just because you can't factor it. This is a way around that. So if you get 0 over 0, then the original limit equals the limit of the derivative of the top and the derivative of the bottom. So you can take the derivative of the top and bottom and then reevaluate the answer. Okay, and this is called L'Hopital's rule. Sometimes they spell it like this, L'Hopital's rule. So there's like an S in there. I don't know. So this also works for infinity over infinity, which is something we're going to start encountering today. Now, I'm not going to talk about how this rule works, why it works. Calc BC, I kind of go a little more in depth into it. But here's a problem from last night's homework that we did, and we had to factor the whole out. We had to do synthetic division, so if you plug 2 in, you get 0 over 0, which is what we got on the homework. And this is your permission to use this rule. So what it says is that you can just take the derivative of the top, 3t squared plus 6t minus 12, derivative of 4 is 0, derivative of the bottom, 3t squared minus 4, and plug the number into this, and you're going to get 12 plus 12 is 24, minus 12 is 12. On the bottom, you're going to get 12 minus 4 is 8, and then your final answer is 3/2. Now compare that to the work we did on the homework, and this was way faster and way easier. Okay, so saves a lot of work. Didn't have to do synthetic. So this is a new rule that we're going to be using sometimes. I'm still going to require you to be able to do it the other way. And by the way, sometimes this is not helpful in the sense of saving work. It can be a lot more work. So it's not like a magic solution that makes everything better. Sometimes it makes things worse, and our other techniques would be better. So now let's talk about end behavior. End behavior is as you go out to infinity, as x goes to infinity. And they call it end behavior because it's way out at the ends. Left end, right end, we're plugging large numbers in. Okay, this is also something we can use to identify horizontal asymptotes if they exist. So, looking at this picture right here, this 1 over x, this is what this function looks like, right? I mean, we've graphed these a lot before as a vertical asymptote at x equals 0. It has a horizontal asymptote at y equals 0. Now, the reason we know that it has this horizontal asymptote is because as x approaches like 1,000,000, like really big numbers, this number gets tiny. It's approaching 0. So this is a whole limit idea. And this 0 right here, that's the y value. And so that's where you get this horizontal line. Okay. Now, here's a different one. If we go to infinity and we plug infinity into this, and what we're going to get is we're going to get really large numbers. Now, I'm going to let you know right now, and I'll explain this in a second. You would get positive infinity over some kind of negative infinity. Now, on the bottom, you have positive infinity minus 6 infinity cubed. Well, infinity cubed is going to be way bigger than infinity, right? So it's definitely going to end up being negative. Now, this is called an indeterminate form. and this is an opportunity to possibly use L'Hopital's rule. I'm not going to do that yet, okay? Because honestly, I can do it quicker another way. Now, back in pre-calc, you guys might have you probably did this kind of stuff. You had to find horizontal asymptotes for rational functions. And you might have just kind of learned the rules, but I don't know either. I don't know if you understood why back then or if you've forgotten it. So I'm going to talk about it again. What I want to focus on are the dominant terms. This only makes sense when we're plugging very large numbers in. Okay, the dominant terms are the terms that are going to get bigger than all the other terms. So on the top, this is the dominant term, 2x cubed, because of that exponent. On the bottom, the minus 6x cubed is the dominant term of those terms. And then between these, one of them might dominate the other. Now, if they're the same kind of size functions, then they're kind of growing together. Now, what we can do is we can essentially just ignore these other terms when we're plugging large numbers in and compare these to each other. And when you do that, you'd be like, oh, well, I'm just going to get, just the ratio of the coefficients, negative 1/3. And that is actually the answer. But why does that work? Okay. Now, for sure, you're going to get negative answer because you have positive infinity over negative infinity. It's definitely going to be negative. It ends up being negative 1/3. So let me illustrate something. This is a way that you can do it. I don't think, you should show this in your work generally because it's a lot of extra work. I could factor out the largest degree term on the top, which is x cubed, right? I'm not going to factor it. I'm going to divide it out. And I'm going to divide the same thing. I can do this with a fraction as long as I do the same thing top and bottom. So what I'm going to do is I'm going to take the biggest x to an exponent and divide it out of everything on the top and everything at the bottom. Okay? We're allowed to do this in math with fractions as long as we do the same thing top and bottom. Now, when you do this, you're going to get 2. So I'm going to, I'm 2 plus 1 over x, and then it's going to be x over x squared minus 6. Okay? Now, as x goes to infinity, we were just talking about this. Doesn't this term get tiny? Doesn't this term get tiny? And essentially it's 2 plus 0 over 0 minus 6. So it's 2 over negative 6. So it's negative 1/3. But this shows you why those terms right there, these other terms, like you might be, oh, but it's infinity squared. That's really big. How can we ignore that? Because here, look at it this way. We can ignore it. It's tiny. It's nothing compared to this. Okay, x squared is nothing compared to 2x cubed. All right. So, now just a little more talk about horizontal asymptotes before we continue. You cannot cross vertical asymptotes, right? But you can cross horizontal asymptotes because it's not an undefined issue. It's an issue of like what's happening as we continue to put bigger and bigger numbers into it. Okay, it's not a division by 0. So I mean, you could have a vertical asymptote and you could have a horizontal asymptote, and then what it could do is it could go like this, and then approach it from the bottom. And sometimes they might cross them over and over again, just continually getting closer and closer and closer to them. So back over here. Let's see. So in this term right here, I wouldn't, I'm going to kind of summarize the results here, but these are not things to memorize because they should totally make sense to you. So here the degree of the top and bottom are the same, and we end up getting the ratio of the coefficients. Now, in this one, we're going to infinity. This is the dominant term. This is the dominant term, so we're going to ignore those, okay? And then compare these to each other. Now, if we just plug infinity in, we're going to get positive infinity over positive infinity. That's an indeterminate form, okay? Then, but what we want to do is we want to compare these to each other. Now, I'm going to argue that the one on the bottom gets way bigger than the one on the top. And so that we're going to actually divide by huge numbers in the bottom compared to the top. And it's going to go to 0. Okay? Now, you might be like, oh, but yeah, bottom's bigger than top, but the top's still really big. Okay, let me just illustrate it again. What if we were to divide out the largest x to a power for the whole fraction, top and bottom? Let's see what happens. This is not work I really want you to show in general because it just takes time, but this should help convince you that we can really just kind of ignore the top when we compare it to the bottom because the x cubed is way bigger than x squared. I'm like, oh no, it's not that. Okay, well let's see what happens here. This is going to be 4 over x minus 1 over x cubed over 1 minus 6 over x cubed. Now, as x goes to infinity, isn't that guy getting tiny? Isn't this guy getting tiny? Isn't this guy getting tiny? Isn't it going to be 0 over 1? So I'm usually not going to show this work. I'm going to be like, oh, this guy is going to blow up compared to this guy. We're going to be divided by huge numbers on the bottom. It's going to go to 0. Now, this next one, here's the dominant term on the top. Here's the dominant term on the bottom. Watch out, the minus is a sign for that. And so if you were just plug negative infinity in, by the way, you get positive infinity over positive infinity because a negative cubed is negative times another negative is positive, and then negative squared is positive. So if anything, one thing I like about writing this is that it tells you the sign of your final answer, which is actually an easy mistake to make. Now I'm going to say, you know what? The top is growing way bigger than the bottom. The top's going to blow up. So we're going to go to positive infinity. Final answer. Technically does not exist, but positive infinity. Now, just to convince you one more time, I'm probably not going to show this again, but just to make you feel confident that this is actually so much bigger than this that we just really essentially must treat this as 0 compared to that. We just ignore these other guys. So if we divide out 1 over x cubed, or multiply 3 by 1 over x cubed, let's see what happens. And this is just, you could do this all the time, but it's a lot of extra work. But I think it's just a way to convince you that this guy is so much bigger than this that this is nothing now, even when we plug infinity in. So if we were to distribute that, this is what we get. So that's 0, that's 0, that's 0, and we get negative 1 over 0, which is, now you might think, oh, it's going to negative infinity. Well, but this is where you have to think let's see, we gotta remember where these came from. Oh, we're going to negative infinity, by the way. I don't know why I forgot that. So then that's going to be positive. Now this 0 on the bottom, remember how we've been doing this recently? It's not really 0, it's something tiny. So which one of these is bigger than the other? I think this one is, but we're plugging a negative, infinity here, and there's already negative, so it's going to be, oh no, that doesn't support my answer. Anyways, it should be positive. I wouldn't necessarily worry about, like I said, we're not going to usually show this work. At the very beginning, we're like, oh, it's definitely positive. For our final answer is definitely positive. Okay. Now, here's something. I'll show you L'Hopital's rule. Now, to use L'Hopital's rule, you can only use L'Hopital's rule if you get 0 over 0 or infinity over infinity. And you should show that. And this is like the laziest way you can show that. On the AP test for your response, you got to get a little more technical with it. So if we do this, then since we've got infinity over infinity, we're going to say, well, it equals the limit as x approaches negative infinity of the derivative of the top over the derivative of the top, over the derivative of the bottom. We plug negative infinity in here, we get positive infinity again over negative infinity, which kind of messes up our answer. No, the top's going to be negative. Okay. And it's still indeterminate. But L'Hopital's rule says you can do it again. So we're going to take the derivative of the top again and the derivative of the bottom again. And now it's going to go to positive infinity over 12, which is positive infinity. So we finally get our answer. But L'Hopital's rule was definitely not quicker, because what we're going to usually do on these problems is we're just going to circle those terms, write the answer. Like, we're not even going to do this work. They're going to be super fast. Now, to summarize our findings, if the degree of the numerator and denominator of the dominant terms are equal, then it's going to just be the ratio of the coefficients. You can get a number. If the denominator is bigger than the bottom, if the denominator is bigger than the top, then it's going to blow up on the bottom. It's going to go to zero. It's going to get really tiny. If the degree of the top is bigger than the bottom, it's going to blow up. The top's going to blow up and you get infinity, positive, negative. And honestly, that's kind of like a slant asymptote, or sort of the graph starts to go towards, it might not be a vertical asymptote. So that's how we do it. Really, you just want to look at dominant terms. So today's assignment is, let's see, we have the back of this worksheet, which has some older problems on it also. This is kind of a review. It has some of the new ones. It does have some. Okay. And this should be a pretty quick worksheet. And then there's this other worksheet that I'd like you to try. And some multiple choice, but you guys show work. And it just kind of has some other stuff thrown in there that we've done before, and just a couple of old, super old, like 40-year-old free response problems on the back. But try these. I think these are mainly just stuff that you guys should be able to already do. They're not really limit problems so much, but just try them out. Okay.